Hello people from the future, welcome to Normalized Nerd. In this video, I'm gonna be talking about a very interesting concept in deep learning, that is autoencoders. Well, when I first learned about autoencoders, then it really made me amazed because it can take a higher dimensional input data, then it can convert it into a lower dimensional code, and we can reconstruct the original input data using this lower dimensional representation of it. Isn't it cool? Well, in this video, first I'm gonna be mentioning the idea behind autoencoders and the math behind it, and then we are gonna see how to build two types of autoencoders. The first one is the normal autoencoder with just an artificial neural network, but the second one will be convolutional autoencoder. So let's get started. The first thing that we need to know is what is encoding. Well, in simple terms, encoding is nothing but the conversion of one type of data into another type of data for the ease of transmission, communication, and storing. Okay, for example, suppose I'm producing sound waves through my mouth, right? And this microphone is catching them as electrical signals. Then, to store this data into my laptop, it has to convert them into digital data because computers can't handle the raw electrical signals. It has to be converted into binaries, that is, into digital data. So, you see, the encoding is happening because we are converting the electrical signal into digital signal. Now, let's come to the autoencoders. Well, an autoencoder has three things. The first thing is the encoder, second one is the code, that is the lower dimensional representation of our input data, and the last one is the decoder that will reconstruct our input data from the lower dimensional representation. The simplest possible autoencoder contains three layers. It is a neural network that contains three layers, okay? So the first layer is obviously the input, and the hidden layer is actually our code. That is, if our input layer contains 784 neurons, well, why this number will be clear into the coding side, okay? Don't worry about it for now. So in the input layer we have 784 neurons, and in the hidden layer say we have 100 neurons, and the output layer we have again 784 neurons. So what do you understand from it? Well, see that in the input layer the number of dimensions is same as the number of dimensions in the output layer. So in a way we are reproducing the input itself. But why does this work? Well, it works because of the universal approximation theorem of neural networks. It says that we can approximate any function using neural network, and we are doing the same. We can imagine this whole coding decoding as a single function. Let me show you how. So here's the architecture of my autoencoder. This is my input layer, which is denoted by X, and this is my output layer, and you can see the dimension of input and output are same, and this layer in the middle is the encoding layer. So to get to the encoding layer from this input layer, we can imagine this conversion as a function f. Why? Because it is a neural network, right? So to get to the second layer from the first layer, what we do? We just apply some kind of linear function, that is, I'm multiplying the weight with the feature, that is the input, and we are adding some bias to it, and after that we are applying a non-linear function. Okay, so f of x is just a combination of linear function and a non-linear function. Okay, similarly, to get to the output layer from this encoding layer, we again apply another function g, which is a combination of linear and non-linear function. Okay, now we are assuming that h is a new function which is just the composite function of g and f. So h of x is equal to g of f of x. Okay, and let me name this output as x dash. So now you know how we can represent the whole neural network as a single function, that is h of x. And according to the theorem of universal approximation, our neural network can actually approximate this function h of x. But how on earth this neural network is gonna learn? Because for learning we need a loss function, and for loss function we need some y value, that is the labels. But here we haven't provide any labels. We just have one input. Okay. So actually in this autoencoders we use this input as the label itself. So in a sense we want to minimize the difference between x and x dash. This kind of models like autoencoders are called as self-supervised learning because it comes up with the output level itself. So a very important point to be noted is autoencoders are an example of self-supervised learners. Okay, now let me show you what loss function do we use here. So there are two very famous loss functions that we use here. The first one is a binary cross entropy, which is very famous and I have discussed a lot about it, and the formula goes something like this. And the second one is the MSE, that is the mean squared error. So we just take the difference between the input and the output, we square this, and then we take the average. Okay, M is just the number of examples. In my coding portion I will actually use both of them. Okay, now let's go back to the picture. Well, one very important thing that you need to know is that the encoding that the autoencoders do is a lossy encoding, which means that we lose some information in the process. You can clearly see that at the beginning we had 784 elements in the input vector, but in the encoded vector we have got only 100 elements, so we are bound to lose something. In this video I'm talking about only two types of autoencoders, that is the vanilla autoencoder and the convolutional autoencoder, but there are actually a lot of autoencoders available. For example, a very famous one is a variational autoencoder, but that is a topic for another video. Okay, so let's jump into the code section. Okay, so fasten your Pythonic seatbelts because we are gonna dive into the programming part of autoencoders. I have put a lot of effort in making this notebook as easily understandable as I could, and you can obviously find the link of this Kaggle notebook in the video description. So be sure to check that, okay? Now I'm gonna show you two things here. The first one is a regular autoencoder, just a simple one, and the second one will be the convolutional autoencoder. For the first one, I'm gonna use the famous MNIST handwritten digit dataset. I know it's a cliched one, but trust me, this is the easiest dataset to apply a autoencoder, and it's a very good point to start this thing. Okay, so the first thing we need to do is to import our dataset, and Keras provides us a very easy way to do that. So for that we just need the MNIST module from Keras library. Then we are going to apply this load data function. So it will give us two things. The first one is a tuple which contains the training set, and the second one is also a tuple which contains the test set. Now you can see that I have replaced the labels with underscore, which simply means that I don't care about those because here I am applying a self-supervised learning algorithm which does not require any labels in the beginning. Alright, so we just need only the features. So now I'm gonna print the dimensions of our training set and test set just to know our dataset better. So you can see that in the training set we have got 60,000 examples, and in the test set we have got 10,000 examples, and this 28,28 just represents the dimensionality of our dataset. So it's clear that we have a 2D matrix with 28 rows and 28 columns. Now we are going to pre-process the data. Well, we know that it is an image data, and we know that the different channels of an image contains numbers from 0 to 255, and this is a grayscale data set, so we have only one channel and the values lie from 0 to 255, so we just normalizing this. Now we are gonna reshape it into a one-dimensional vector. As you notice here that the dimension here is 28,28. Now if you multiply them you will get 784. So you can see that we are converting our 2D feature into one-dimensional vector of length 784. Now let us visualize the digits. Well, for the visualization purpose I have written this little function here which is called show data. Now I'm not going to explain this function because it's really implementing some matplotlib code. You can find it on the internet easily. So the parameters are here obviously what we want to visualize, then how many of the set we are going to visualize. So default value is 10. Height represents the height of the output image, and the width represents the width of the output image that our function is gonna show. And I have included a argument called title, which will just give us this effect. Okay, so we will know what we are actually plotting. So let's plot them, and I need to mention one thing here, that this show data function will be helpful in our next part also. Okay, so here is the representation of our dataset. Now let's build the autoencoder. Okay, so to build the autoencoder, as I have told in the conceptual portion, we need three main things: an encoder, the code, and the decoder. So we have to first mention the dimensionality of these things. So obviously input dimension and output dimension will be same. Now the encoded dimension here is 100. So you can easily see that it is compressing our data nearly 8 times of its original size. There is another thing called hidden dimension. Well, this is just the dimension of the hidden layer. So to build the encoder, we need to use neural networks. And in Keras, to provide the input layer of a neural network, we use this input function. And the shape will be input dimension, comma, nothing. Well, this means it is 1D vector, okay? And the name is input. Well, I am naming these layers just for the ease of accessing them, okay? Now comes the hidden layer. It will be a dense layer. Well, I'm working with vanilla neural network, so every node of the previous layer will be connected to every node in the next layer. That's why dense layer. Now for the code layer, we are also going to use dense layer, and you can see that activation I'm using is ReLU, which is rectified linear unit, which works really well. Okay, and here we have the decoder portion. We are gonna take the code layer and we are gonna feed it to the hidden layer. Then we have the output layer. Now here one interesting thing is that I am using activation as sigmoid. So we have built our model. Now let's compile it and see the summary, which is just seeing the architecture. Now let's train our autoencoder. Okay, so training is very simple to do here, and it takes really just a couple of minutes. The interesting thing here is we are passing xtrain 2 times. Usually we would pass xtrain and ytrain, but here as we are generating the input itself, so we have to pass this xtrain 2 times here. So the loss is really low, and after 10 epochs you can see that the loss is 0.0692. Okay, now we are gonna see the results, but first we need to do some things. Well, the first thing is we have to get the reconstructed data. How to do that? Just use the .predict function, and you see here that I have used xtest, so I'm visualizing the results on xtest. Okay, and then we need to do something interesting. We have to make a model that will give us the encoded representation. Well, we are making a new model, but what we are actually doing is we are just making the half model of our actual model. So you can see here that I am making a new model named get encoded data, and the inputs will be the same as our previous model input, but the output will be the code layer. So you see that naming the layers is helping us now. Okay, so now let's visualize them. Hold your breaths. You just see that this is our original data and this is our decoded data. So you can clearly see how good the model is. And if you just look at casually, you can't even see if they are different. Only if you look minutely, then you can find some things. Just like, see here, here is just a little thing here in the 9, but in the reconstructed 9 we don't have that. Okay, so that was the vanilla autoencoder. Now I'm gonna show you how you can build a convolutional autoencoder. Well, the data I am taking here for convolutional autoencoder is the famous cat versus dog dataset. Now I am using only half of it, that is I am using only the cat images. Okay, so this is a Kaggle kernel. So you can just visit that Kaggle link and you will know how the dataset is stored in Kaggle and how to retrieve that. Okay. As usual, I'm gonna print the shape of our dataset. So in this case, you can see that the dimension has increased by 1. Well, obviously because these images are RGB images. So we must have 3 channels for the 3 colors. And the dimension of each image is 128 pixel by 128 pixel. Okay. So again, we are going to visualize our data. Now, in this case, I am actually using an other visualization function, and the previous visualization function will also be helpful, but it will come a bit later. Okay, so to visualize the RGB images, I'm using this function called show cat data, and this is what we are feeding to our this function and how many of the set we are gonna show, and obviously the title. Okay, so after running this we will get this. So these are our train cats, obviously the first 10 of them, and these are our test cats. Let's build the convolutional autoencoder. Okay, so it seems lengthy, but it's really not tough. Okay, so the first thing we need to have is the input, and the input is just our RGB images. So the shape is 128, 128, 3. Now we are gonna use something called convolutional layer. Remember that convolution layers are very good in learning features from an image data. And you can see here that I'm using padding same. So that means that after convolution, the dimension of the data won't change. Well, it will increase in depth. At first we had only 3 channels, but after this convolution the depth will be 16, but the dimension of one channel won't change. It will remain 128 by 128. Okay, so the next layer is max pooling layer. Now this layer doesn't contain any parameters. That means it won't learn anything, but it will do a very important thing. It will decrease the dimensionality of our features, the spatial dimensionality actually, not the depth. Okay, then in the next layer I'm again using a convolutional layer, and then again a max pooling layer, and then again a convolution layer. And this is the layer that is very important for us, which is the code layer. This layer is actually the compressed representation of our data. You can see here we are using here something called as conv 2D transpose. Now many people mistakenly thinks that conv 2D transpose is an inverse function of conv 2D, but it's really not. Transposed convolution is actually the same as convolution. It's just the case that in transposed convolution we change our input feature according to the padding and stride. If the padding is same, then conv 2D transpose is exactly same as conv 2D. Okay, and that is what I am using here. So you can easily use the conv 2D layer instead of conv 2D transpose. And after that we are using a layer called upsampling 2D. Well, this is kind of an inverse function of max pooling 2D, because in pooling we were decreasing the spatial dimension, but here we are increasing the spatial dimension. Then again I am adding a transposed convolution layer, then again an upsampling layer, then again conv, then again upsampling. So I'm doing that just to maintain the mirror of the encoder thing. But as you know, it is not necessary that you use the exact same mirror architecture of the encoder, but I think it's really cool to implement the mirror version of the encoder layer in our decoder. Now at last you will see that we have to add this conv 2D with a depth of 3. Can you guess why? it is because we want to reproduce the RGB images. So this was our convolutional autoencoder for cat images. Now let's see the cooler representation of this model. Now we are just gonna compile this, and after this we are gonna train this thing. I will recommend to use a GPU here, and Kaggle offers free GPU, so you can use that obviously. You can see that my training loss and validation loss are really close to each other. That's a great thing. So to reuse this model, I would recommend to save this, and then again we have to get the encoded representation, and for that we need to make another model, well, just the half of the previous model. So inputs will be same as the cat AE, but the outputs will just be the code layer. Now I am getting the encoded cats just like that. Now here's one thing, that the code layer of my model was having depth of 8, and each feature was of the dimension 16 by 16. Now for the ease of working, I'm actually converting them into a one dimensional vector which has 16 times 16 times 16 elements, that is 2048 elements. Okay, now let's get the reconstructed cats. Well, you can get this by our original cat AE model and use the predict method. So now the most exciting part, we are gonna visualize this thing. Just one thing before that, see here that to visualize the RGB images I am using this show cat data function, but to visualize the encoded data I am using the previous show data function. And here I am passing the height as 32 and width as 64, which will help us to visualize this thing better. Okay, now let's see this. This is our original cats, and remember that I am doing this on test set. Okay, and this is our encoded cats. Well, I couldn't make them align properly, but you can guess it, right? This corresponds to this and this corresponds to this. Okay, now let's see the reconstructed cats. Here you can see that they are very recognizable. Obviously they are not exact reconstructed things because I am compressing the data 24 times and then reconstructing it, but you can recognize the cats from the reconstructed images, aren't you? And this black cat is also recognizable very easily. Now I'm going to tell you a couple of important things about autoencoder. Well, few years ago when this was a hot topic in research, many people thought that this has a potential to do a lot of things. And it is true that we can use autoencoders in a variety of applications like image segmentation, image denoising, data compression, dimensional reduction for better visualization, machine translation, image generation, and the list goes on. But eventually we have found better models in most of these applications. So autoencoders are kind of a jack of all trades in deep learning. We can do a lot of things with it, but it can't produce the best results in any of them. So I would suggest you to learn autoencoder as an interesting topic in machine learning rather than a practical model that you will be applying in real world, because we have better models for that. Okay, so that was all for this video. I hope you have liked this video on autoencoders. Please share this video if you have liked this and subscribe to this channel for more interesting videos on machine learning. Stay safe and thanks for watching.